Today we are very happy to have Muldrow of Etheredge from UMass Amherst, and he will talk about dense geodesic tower alignment, and the sharpened distance conjecture. So please go ahead.
All right. Well, thank you to the organizers. Yes, today I will be talking about a paper that came out in August with this title, Dense Geodesics, Tower Alignment, and the Sharpened Distance Conjecture. The distance conjecture and the scalar weak gravity conjecture are related but distinct conjectures. When moduli spaces are flat and scalar charge-to-mass ratio vectors don't slide around as you move around in moduli space, these two conjectures imply each other. However, when moduli spaces are not flat and when scalar charge-to-mass ratio vectors slide around, these two conjectures do not imply each other anymore. In this talk, I will try to reconnect these two conjectures by proposing two new conjectures that deal with non-flat moduli spaces and when scalar charge-to-mass ratio vectors slide around. The first new conjecture I'll propose is the dense directions conjecture. This conjecture states that at each point of the moduli space, if I consider the collection of geodesics that pass through that point and go to infinite distance limits, this collection of geodesics passes through the point in a set of directions that is dense in the tangent space at that point. The other conjecture I'll tell you about today is the tower alignment conjecture. This states that for each geodesic going off to an infinite distance limit in moduli space, there exists a tower whose scalar charge-to-mass ratio vector projected along that geodesic everywhere along that geodesic is greater than or equal to 1 over square root of d minus 2, where d is the number of space-time dimensions. So these two conjectures, I'm going to argue, reconnect the distance conjecture and scalar weak gravity conjecture for non-flat moduli spaces. Along the way, I will also highlight the role of scalar charge-to-mass ratios and how they are connected with moduli space geometry. Let's begin with the distance conjecture. If you travel a far distance delta down an asymptotic spike in moduli space, then you will encounter a tower of light particles with masses that get exponentially light with the distance you travel in. The sharpened distance conjecture says that at least one of the towers will be so light that the alpha is greater than or equal to 1 over square root of d minus 2, where d is the number of space-time dimensions. This sharpened distance conjecture bound, which appeared in this paper last summer, is motivated by three things. One, it is satisfied and often saturated in every string theory example that we checked. Also, it is a special bound that is selected by dimensional reduction. Lastly, it fits very, very nicely with the emergent string conjecture. If you assume certain things about the towers in emergent string limits or decompactification limits, then you get this bound, provided that you assume some things about those towers. So this is the sharpened distance conjecture. It's an asymptotic statement in moduli space, whereas the scalar weak gravity conjecture is a local statement in moduli space. But before I tell you about the scalar weak gravity conjecture, I need to tell you about scalar charge-to-mass ratio vectors. So if you give me a particle with some mass that depends on the scalar fields, if I take minus the gradient of the logarithm of that mass, I have the so-called scalar charge-to-mass ratio vector for that particle. Now, if this particle is defined everywhere in the moduli space, then this gives me a vector for each point in the moduli space. With these vectors, I can now introduce the scalar weak gravity conjecture, or tower scalar weak gravity conjecture. This conjecture states that the convex hull of scalar charge-to-mass ratio vectors for towers contains a ball of radius 1 over square root of d minus 2. So for instance, here are various scalar charge-to-mass ratio vectors for towers, and their convex hull contains a ball of radius 1 over square root of d minus 2. So this conjecture has undergone various different forms throughout history. Originally, Palti had an inequality conjecture about scalar charge to mass ratios, not vectors, just ratios. And then in this paper in 2020, a convex hull condition was introduced. And in this paper from 2022, the convex hull was found to contain the ball of radius 1 over square root of d minus 2. In my paper from August, I emphasized that technically it's actually just the closure of the convex hull that contains the ball, not necessarily the convex hull itself. Sometimes you can have points on the boundary of the ball missed by the convex hull of scalar charge to mass ratio vectors. In this talk, I will refer to the Tower scalar weak gravity conjecture as just the scalar weak gravity conjecture and refer to this statement moving forwards. So the scalar weak gravity conjecture was observed to be very closely related with the distance conjecture. In fact, in many cases, they are codependent. So for instance, take M theory on an orthogonal 2 torus, and let's ignore axions for now. So in this case, let's just look at the radion-radion moduli space. In this case, the radion-radion moduli space is just R2, and this is flat. Now, if we plot the scalar charge to mass ratio vectors, their convex hull looks like this. Now, if we go in any infinite distance limit in this moduli space, any direction, because we have the scalar weak gravity conjecture, there will always be a scalar charge to mass ratio vector whose projection along that direction is greater than or equal to 1 over square root of d minus 2. Well, that means that we can integrate. So the scalar charge to mass ratio vector gives us a differential equation governing the mass. And we can integrate this differential equation along any infinite distance limit in this case. And we can get back precisely the Sharpened distance conjecture bound. Also, or we can get the Sharpened distance conjecture. Also, conversely, if we assume that this figure doesn't change shape and doesn't deform as we move around moduli space, and we assume the Sharpened distance conjecture, then we get back the scalar weak gravity conjecture. So in this case, the scalar weak gravity conjecture and distance conjecture are codependent. Actually, we can, just as an aside, we can go a little bit further. If we assume the emergent string conjecture, then for any infinite distance limit, we have decompactification or tensionless strings. We can further constrain figures like this. It turns out that assuming the emergent string conjecture and assuming that the scalar charge to mass ratio vectors don't slide and the moduli space is flat, forces these vertices to correspond to either KK modes or string oscillators. And in an upcoming paper, hopefully coming out in the next month or so, we use the emergent string conjecture to get a set of rules for polytopes like this in these situations. And we have some rules for vertex lengths and facet shapes and angles. And we provide a taxonomy for such types of polytopes. I also want to point out that these polytopes also constrain the asymptotics of the species scale. Using some not yet published work from a Madrid collaboration involving Irene Valenzuela, and also in an upcoming paper, we find that the reciprocal duals of these polytopes tell you about the decay of the species scale in various different directions. So a taxonomy of these polytopes also gives us a taxonomy of the asymptotic decay of the species scale. Anyway, so the takeaway here, though, is the scalar weak gravity conjecture and the distance conjecture are codependent when alpha vectors or scalar charge to mass ratio vectors are fixed and the moduli space is globally flat. However, alpha vectors often slide, even in flat moduli spaces. For instance, this was explored in this paper for heterotic string theory on a circle when looking at just the radion dilaton moduli space. Scalar charge to mass ratio vectors slid around, even in this flat moduli space. So if you translated the convex hull of scalar charge to mass ratio vectors changed shape depending on where you were in moduli space. Also, moduli spaces are rarely flat. It's only, most of the time, it's only certain special slices of moduli space that are flat. Generically, moduli spaces are not flat. So, in general, the scalar regravity conjecture does not imply the distance conjecture. So for non-flat moduli spaces, or when alpha vectors slide around, the distance conjecture is not implied by the scalar regravity conjecture. Well, this can be somewhat disappointing if one was hoping that the scalar regravity conjecture was a local version of the distance conjecture. So what are we to make of the scalar regravity conjecture and distance conjecture? How are they related? They're related in flat moduli spaces when alpha vectors don't slide, but otherwise, how are they related? Also, with this sliding, what are we to make of it? So for instance, here are collections of scalar charge to mass ratio vectors for PQ strings in 10D2B string theory. These are various PQ string oscillator alpha vectors at different points in the moduli space. Notice that they've arranged themselves differently at different points. So these scalar charge to mass ratio vectors slide around in the tangent space as you move around. What describes this sliding? What are these scalar charge to mass ratio vectors pointing at? Spoiler alert, these scalar charge to mass ratio vectors are actually pointing along geodesics that go to infinite distance limits. But anyway, so what are we to make of these two conjectures? How can we reconnect them for non-flat moduli spaces? Well, I'm going to propose two new conjectures. First conjecture is what I call the dense directions conjecture. So for every point phi in the moduli space, the set of geodesics that pass through phi and also go to infinite distance limits pass through phi in a set of directions that is dense in the tangent space at phi. So this conjecture is just a conjecture about the geometry of moduli spaces. This so far has nothing to do with particle spectra or scalar charge to mass ratio vectors. The next conjecture I'm going to propose is what I call the tower alignment conjecture. So for every geodesic going to an infinite distance limit, there is a tower with an alpha vector, or scalar charge to mass ratio vector, whose projection along that geodesic is at least 1 over square root of d minus 2 everywhere along that geodesic. Now, this tower alignment conjecture is a very strong form of the sharpened distance conjecture. The distance conjecture requires tower alignment only asymptotically down a geodesic. However, this tower alignment conjecture is requiring alignment everywhere along the geodesic. Now, this may make you nervous, and it should. For instance, sometimes this requires that towers of non-BPS states align with geodesics. And perhaps you are worried about stability, as one should be worried. Turns out you can have heavy non-BPS states. So in defense of this conjecture. In my paper, I discussed several weaker versions or alternative versions of the tower alignment conjecture to deal with some of these issues. However, this version, this tower alignment conjecture, is satisfied in the examples I've thoroughly checked. And in fact, this version combines with the dense directions conjecture to give the scalar weak gravity conjecture. Some weaker versions of tower alignment do not give the scalar weak gravity conjecture. So the way this argument goes is with the dense directions conjecture, if I pick any direction in the tangent space, I can find an infinite distance geodesic arbitrarily aligned with that direction. And the tower alignment conjecture says that there's an alpha vector who's sufficiently aligned with the geodesic that's sufficiently or arbitrarily aligned with the direction I picked. And those two properties together give you the tower scalar weak gravity conjecture. So these two different conjectures do give together the scalar weak gravity conjecture. Now I will demonstrate how this happens in several examples. So the first example I will breeze through because it's relatively trivial in that the moduli space is flat and scalar charge to mass ratio vectors don't slide. So that's 2A string theory in 10D. Here there's just one modulus, which is the dilaton. well, they're just two infinite distance geodesics, or limits. Radion goes to plus or minus infinity. And sure enough, there are scalar charge-to-mass ratio vectors that align with these two geodesics. So in this case, the moduli space is flat, so it's not a very strong test for my two conjectures. But my two conjectures hold in this case. A tough test for my new conjectures is 10D 2B string theory. So in this case, there is just the axio-dilaton moduli space, which I've written with this complexified tau. So this space is the Poincare half-plane quotiented by SL2Z. And the fundamental domain is this keyhole region that hopefully many of you all are familiar with. And the metric on this space is the Poincare half-plane metric. In this case, there's only one infinite distance geodesic, only one infinite distance limit. And that limit is just going vertically up this region infinitely far up. That's the only infinite distance limit. However, there are many geodesics that take you there. So you could have a geodesic that goes just vertically up and goes there just vertically. You could also have a geodesic that maybe starts here, passes through one side of the fundamental domain, reappears at an identified side, passes through another side, and then reappears at another identified side, and then ends up going up. You could have very complicated geodesics that pass through multiple identified sides and eventually go straight up. That's a little bit overwhelming to think about, but you can consider the Poincare half-plane covering space. And it turns out that the infinite distance geodesics are semicircles that pass through rational points on the x-axis, and they pass through these points vertically. Now, with this perspective on the infinite distance geodesics, in fact, the dense geodesic conjecture is apparent. You can sort of see it here. Here, if I'm at the point here, and considering all of these geodesics, infinite distance geodesics, you can see that the dense directions conjecture is satisfied. So at this point here, the set of infinite distance geodesics passes through this point in a set of directions that is dense in the tangent space around this point, or at this point. So in this case, the dense directions conjecture is satisfied. How about the tower alignment conjecture? Well, in this theory, there are only one type of tower, which are oscillator modes for PQ strings. If you assume that the masses of these towers scales with the square root of the tensions of these PQ strings, so this is the tension of the PQ string, then the scalar charge-to-mass ratio vectors for these PQ string oscillators takes this form, is given by this formula. So I can plot these PQ strings at the point, I guess, tau equaling I. And here are some of them. So all of these PQ string oscillators have length precisely 1/square root of d minus 2. And you can see that the scalar weak gravity conjecture is satisfied, because if the closure of the convex hull of all of these contains the disk of radius 1/square root of d minus 2. All right, so the tower alignment conjecture requires that for each infinite distance geodesic, each geodesic going to an infinite distance limit, I need a scalar charge-to-mass ratio vector such that the projection of that scalar charge-to-mass ratio vector along that geodesic is at least 1/square root of d minus 2. And these scalar charge-to-mass ratio vectors have length exactly 1/square root of d minus 2. So if the tower alignment conjecture has any hope of being satisfied, I need for each infinite distance geodesic, infinite limit geodesic, I need a scalar charge-to-mass ratio vector to be perfectly aligned with that geodesic, to be parallel with that geodesic, everywhere along that geodesic. In fact, I need the geodesic to be the gradient flow solution for one of these scalar charge-to-mass ratio vectors. Now, that's a very tall order, but It turns out that this is exactly what happens. In fact, the gradient flows of these scalar charge to mass ratio vectors themselves, in this case, are geodesics. So if I take the gradient flow for a PQ string oscillator, it will take me to the point minus P over Q on the x-axis. And since I can vary P and Q, I can get every rational point on the x-axis as the gradient flow as the location of where a gradient flow goes for a PQ string oscillator. So in fact, the tower alignment conjecture is satisfied in this case. And I really want to emphasize how close it comes to not being satisfied. If you didn't have this gradient flow property, tower alignment would fail. But remarkably, it survives in this example. So for instance, here are some PQ strings aligning with these geodesics. If I move this starting point, you would see that these arrows still align with these geodesics. So in this case, tower alignment and dense directions conjecture are satisfied. And as a consequence, scalar weak gravity conjecture and distance conjecture are also satisfied. We can also go put this theory on a circle and consider the 90 theory. Here, the moduli space is just the radion times the axiodilaton moduli space from 10D 2B string theory. So the geodesics are given by two parameters, the infinite limit geodesics, theta, which tells you roughly the angle of travel in this radion space versus axiodilaton space, and q, which tells you which rational point on the x-axis of the Poincare covering space of this axiodilaton moduli space you're going to. You can also add constants to affect the starting points of these geodesics, but that doesn't affect this discussion. So the infinite limit geodesics are given by a two-parameter family of geodesics. It turns out, as is explicitly demonstrated in the paper, these geodesics satisfy the dense direction conjecture. For each point in this moduli space, if I consider a direction in the tangent space at that point, I can find a geodesic that is sufficiently aligned or arbitrarily aligned with that direction. So the dense direction conjecture is satisfied. How about tower alignment? Well, for this theory, the quarter BPS alpha vectors were computed in a paper from last summer. Here's a plot of some of them. They end up living on a cone, and this cone contains the ball of radius 1 over square root of d minus 2. Do any of these quarter BPS states align with these infinite distance geodesics? Well, it turns out we can consider just the half BPS states. And in fact, we can, for each infinite distance geodesic, find a half BPS scalar charge to mass ratio vector such that it aligns everywhere along the geodesic with that geodesic in a way so that the tower alignment conjecture is satisfied. I want to point out that this inequality sometimes comes very close to failing. Sometimes, for some angles theta, sometimes this inequality is saturated. And for reasons similar to the 2B and 10D example, this conjecture comes very, very close to failing. But the tower alignment conjecture once again survives in this example. Another example to consider is heterotic string theory in 9D. So I performed some limited tests. This involves sliding, but this is work in progress because the moduli space is high dimensional and one needs to keep track of non-BPS states. This is work in progress. So scalar charge to mass ratio vectors are connected with the geometry of moduli space, as you could see in the 10D 2B string theory example. In fact, it turns out whenever an alpha vector has constant length, the alpha vector generates a geodesic gradient flow. This is to appear in work maybe coming out in a month or two with Ben Heidenreich. So the proof is very quick. suppose that the alpha vector has constant length, and let phi be a solution to the gradient flow equation. Then if we plug in phi into the geodesic equation combination, it becomes proportional to the gradient of the length of the alpha vector, which is constant, so this is 0. So in fact, solutions to the gradient flow equation are geodesics when alpha vectors have constant length. It is very common for alpha vectors to have constant length. This happens, for instance, for all of the half BPS states in maximal supergravity in dimensions 4, 5, 6, 7, 8, 9, and 10. This also happens for string oscillator modes. This also happens in various 16 supercharge examples that I'm aware of. So this is a way to unlock many geodesics and probe moduli space geometry. But much remains to be investigated about these alpha vectors. Where do these gradient flows ultimately go? Also, it's interesting to compute divergences of these alpha vectors. Often these are remarkably simple numbers like 0 or 1. So the logarithms of masses of various particles often satisfy Poisson's equation with remarkably simple inhomogeneous terms. Finally, another thing to investigate about these alpha vectors is they connect moduli space geometry, or they're connected to moduli space geometry, but they also play prominent roles in the species scale. You saw that the reciprocal duals of the scalar regravity conjecture polytope tell you about the decay of the species scale. They also appear explicitly in the long-range force formulas in the repulsive force conjecture. And it also seems that the weak gravity conjecture is a necessary condition for the scalar weak gravity conjecture to be preserved under dimensional reduction. So these alpha vectors play a big role in connecting moduli space geometry with particle spectra, and they also appear a lot in objects of swampland interest. Okay, in summary, the scalar weak gravity conjecture are independent. They are codependent in moduli spaces that are flat and when the scalar charge-to-mass ratio vectors don't move or slide around. But they are independent for moduli spaces that are not flat and when scalar charge-to-mass ratio vectors slide around. To reconnect these two conjectures, the scalar weak gravity conjecture and distance conjecture, I've proposed the dense directions conjecture and tower alignment conjecture. As together, these conjectures imply the sharpened distance conjecture and scalar weak gravity conjecture. Lastly, I think that alpha vectors will play a large future role in charting moduli spaces and connecting moduli space geometry with brane and particle spectra. Thank you.
So thanks a lot, Muldrow, for this very interesting talk. So we have already one question. So please, you can unmute yourself. Yeah.
Yes, so that was a very interesting talk. I have a question about the alpha polytopes that you mentioned. And you mentioned the heterotic higher dimensional case. Usually, sometimes polytopes have a group structure that they use to classify them in higher dimensions. Is there any kind of group or discrete group structure associated with these alpha polytopes?
Oh, that's a really, really good question. Yeah, I've really wondered whether there's a group structure associated with these polytopes. I know that Ignacio Ruiz is investigating this, but I haven't yet figured out. So often these polytopes do have a lot of symmetries with them. And I think it would be very interesting if there was a group structure that provided a deeper understanding for them. Yeah, I don't know though for sure whether or what the story is there, but that's a very interesting question.
Yeah, I'd be interested to see your heterotic analysis eventually, because the higher dimensional cases is where that's really very useful.
Right, yeah. In upcoming work, we're looking at, for instance, the polytopes for M theory on tori and considering just the radion directions. And often these polytopes do have a lot of symmetry with them. And I know Ignacio has been looking into connecting this with, I think, U-duality. And yeah, I think in heterotic string theory, it would be interesting to connect the symmetry there with the polytope structure.
Yes, at least in the cases that we have checked, which is the toroidal compactification of M theory, these polytopes, the symmetries that they have are the Weyl group of the dualities of the supergravity. So yeah, you get like you are like quotienting out the compact part of the duality group, which would be like the actions, and then like the radians, the symmetries that they have are given by the Weyl group of the supergravity U duality group. But apart from that, I don't think we have a lot more to say like that we know for sure that's happening.
Thanks.
Okay, we have another question by Jose, the last question, and then we go to the next speaker.
Hi, can you hear me?
Yes.
Yes.
Yeah, thanks a lot for the talk, Muldrow. So I have a couple of questions. Let me try to be quick so that the chairmen don't get annoyed. One is about the first conjecture is telling me that at any point I should have a geodesic passing through any direction. If the moduli space is a manifold, then the fact that locally I have a flat space, I know that there will be a geodesic for any direction because it's locally flat. Then if I understand correctly, the non-trivial part of your conjecture is that at least a dense set of them can go to infinite distance somehow.
Yeah.
Okay, so it's more something global rather than something local in the moduli space.
Yeah. This is a statement about the geodesics that go to infinite distance limits. So it does involve global stuff.
Okay, good. And then about the second conjecture is telling me that if I have any geodesic going to infinite distance, then there should be an alpha vector such that if I project it, I get something bigger than the sharpened. How is that different to the distance conjecture itself?
So good question. Yeah, so the distance conjecture requires this just asymptotically along the geodesic.
Mm-hmm.
So as you're going far down an infinite distance spike. What I'm proposing is that this holds everywhere on the geodesic. So if you backtrack along the geodesic.
Okay, that's very strong. So you are saying that
strong,
for any
yeah.
geodesic, even in the very, very interior of moduli space, at any point there will be something falling more than exponentially with that, right?
Yeah.
Okay, thank you. Thanks.
Okay, so we thank again Muldrow